Good afternoon, everyone. Time for some combinatorics. Hopefully that's exciting news for you. It certainly is for me. So we're going to continue our discussion of the chapter 9 material, with our goal being eventually to get to Polya's formula. You don't know what that is yet, but you do know this. You do know Burnside's theorem, no doubt. Okay, that is something that we spent a lot of time hashing out. And we remarked last time that it's really this second formula that's generally the easiest to deal with, okay? Namely, counting the number of colorings that are fixed by a given permutation is generally a simpler thing to do. So our goal is going to be to compute this quantity in a more efficient way. That's going to be our goal today, all right? So one thing I want to point out is all of the theory that undergirds Burnside's theorem didn't really depend on the sorts of things that we were coloring. We could be coloring vertices, we could be coloring edges, and we can even color things in a specific way. So for instance, you know, I might require that all of the colorings on the vertices be different colors. Okay, so I might do that. I might actually first color the vertices differently and then allow for a group to operate on this thing. And all of this theory that we came up with would still apply. So all I need is to have a group, right? And it might not be all possible symmetries of a given shape even. It just has to be a group. There has to be an identity element. The composition of any two of the permutations that operate on our objects have to again be an object of the group, and I have to have inverses. Those are the requirements of the group of operations, the group of symmetries that we're looking at. I don't have to have them all, it just has to be a group. And the colorings can be a very specific kind of coloring, and the number of colorings doesn't really matter either, or the number of colors doesn't really matter, okay? I can have 2 colors or 3 colors, whatever you want. And all of the theory still applies. If you go back and you look at everything, you'll realize, oh man, none of that, it didn't matter that there was 2 colors. It didn't matter that I was coloring vertices. I could have been coloring edges. It didn't matter that I allowed anything at all at any one of the vertices. This theory applies widely, and that's to our great benefit. No doubt about it. Okay, so and let me just mention, I said this in an email, but the next homework set won't be due until the Monday after this weekend. Okay, so that's a week from today, April 13th. That's stuff from 9.1 and 9.2. I think that maybe the last homework assignment might just be a combination of 9.3 and 9.4. The next 2 homework assignments are 9.3 and then 9.4 respectively. Those are really short. I might just combine those 2 into one and have you turn that in as a last homework assignment. Again, I just really want to digest this chapter 9 material. Chapter 10 is something we just simply will not get to in this class, but it is something that I will do in my capstone seminar, namely the theory of combinatorial games, which will be a good time also. Okay. So again, our goal is to figure out how to deal with this psi of pi thing. How in the world do I systematically count the number of colorings that are fixed by a given permutation? And it turns out that might be a little bit easier than you might think. Okay. So let's have a look here. This was us doing a couple of computations last time that we went through, but the big concept for today is this thing called the cycle index, okay? And the cycle index is going to aid in our computation of psi of pi for a given permutation pi, okay? So we want an easy way to do this, so here it is. So given a permutation and a coloring, think about it for a second. A specific coloring is going to be fixed if and only if all vertices in the same orbit are the same color, okay? And by orbit, orbit is just it's analogous to a cycle. Okay, so if I have a couple of vertices or edges or whatever it is you're looking at that are being colored, and they happen to kind of move around in a cycle, if they move around in a cycle, then the only way that that coloring is going to be fixed is if everything in that cycle is the exact same color. So once I choose one of those, we're done. And once I choose one color for that, the rest have to be that same color. That is exactly what was going on with that triangular arrangement of 15 balls that we did at the end of last time, my friends. We had several balls that all had to be the same color in order to be fixed by a given permutation. Those balls were all in the same cycle or circuit or orbit, whatever you want to call it. Okay? So you should think of an orbit as one unit. And once I've colored one of those things, all those other things have to get the same color so that I can't distinguish it when I happen to rotate the thing around or reflect it or whatever. Okay, how many orbits are there? Okay, that's going to kind of be the key question that we're going to have. If we have k colors, then each orbit in a given permutation that's acting on a coloring gets exactly one color. And since I have k choices, that one orbit contributes a k. So basically what this is, so this is k times k all the way to k, right? So this is number of orbits in pi. Okay, so what we're doing here is we just put a color on each orbit, on each cycle or orbit. Okay, that's exactly what's going on here. Put just one color, and since that thing is going to rotate around to everything else, that same color needs to be put on all those other things as well. Okay, so let's go back to our old friend, the square. Okay, let's go back to our old friend, the square here. And I've just kind of quickly sketched this. So the idea that I have in my mind is, okay, so here's our square, and I'm labeling the vertices. This is A, this is B, this is C, and this is D. Okay. So 0 degree, well, A goes to A, right? That's the identity rotation. A goes to B, B goes to C, which is what this second thing is, right? A goes to B, B goes to C, C goes to D, D goes back to A. Remember how this works? Right? We kind of go like this. A goes to B, which goes to C, which goes to D, and then D goes back to A. That's how the cycles work. So that's 90-degree rotation, right? A is going to B, B is going to C, C is going to D, and D is going back to A. Okay? So that's what's happening with that particular one. Okay, let me get rid of those few last little markings that I did. Okay, and then AC, okay, 180-degree rotation. Of course, A and C are going to flip back and forth between one another, and same thing with B and D. 270-degree rotation, that's the same thing as backwards rotation by 90 degrees. So that's just A go to D, D go to C, C go to B, and B go to A. Okay. And then I have this vertical line, which is reflection in the vertical axis like this. So that means that A goes to B and B goes to A, C goes to D, and D goes back to C, yeah? Okay, and then reflection in the horizontal axis, well, that A and D are gonna flip back and forth and B and C flip back and forth. And then the negative slope line, right, the negative slope line, okay, if I have the negative slope line, A and C just stay where they are, but B and D are going to flip back and forth. And then finally, the positive slope line, AC flip back and forth, and B and D stay fixed. Okay? And then so remember what we did here, and we've already kind of done this computation. Let me clear this thing. We've done this computation before, but I just want to think about this. Let's think about the structure of these permutations. Okay? So How many things are fixed? Remember, I was working with two colors. Okay, the two colors were black and white in the problem that we were working on before. Okay, so I had two colors. So basically, I can kind of stare at these orbits individually. So what about, okay, so what about the identity permutation? Well, how many options do I have for colors on A? If I want it to be fixed by the identity permutation? Well, I can put any of two colors on that cycle, two colors here, two colors here, and two colors here. 2 times 2 times 2 times 2. Okay? And that's it. So that's 2 to the 4th, which gives rise to that 2 to the 4th right there. Okay? Now, what about A, B, C, D? Well, that's one giant cycle, right? That's just one giant cycle. So the minute I decide what A is, okay, I have two choices for A. The minute I decide what A is, everything else has to be colored that same color. Okay, so that's I only right. So there's only two things going on here. So that's one of those. Okay, so it's basically saying how many colorings are going to be fixed by this. Well, I just decide what A is, namely white, and all the rest of them have to be white. Okay. So that's going to be either the all white vertex square or the all black vertex square. Okay. What is the other one? What's the one that's contributing the other two? Because it's 2 times 2. Well, it's this guy right here. Okay. That thing that's a complete cycle, that contributes the other two, which gives me the 2 times 2. Okay. So what about ACBD? Okay. Well, ACBD, again, I have two options for the first cycle and two options for the second cycle, namely black or white, black or white. Okay. So black or white for A, so once I know what A is, if it's black, so C has to be black also in order for this thing to be fixed. So that's 2 times 2, okay, which corresponds to 2 squared, which is one of those. And of course, this guy right here corresponds to one of those. And is there another one? Yeah, this guy right here corresponds to one of those, which is why there are three total, there's three total, permutations. There's three total permutations of this sort, and each one has 2 squared colorings that they happen to fix. I'm counting the number of colorings that are fixed by these things. Okay. So, and finally, what's going on with these last two? Well, okay, so this is 2 times 2 times 2, all right? And that gives rise to that, right? So that's the number of colorings that are going to be fixed by that permutation, 2 cubed. And then same thing here, 2 times 2 times 2. That's the number of colorings that are going to be fixed by that particular permutation. Okay, so overall, we get 16 plus 4 plus 12 plus 16, okay, which is 48. Okay, I think so. Let's see here, 20 and 28 is 48. Divided by 8 is 6. Remember, the total size of the group was 8, right? Just count the number of things over there. Okay, so all we're doing is we're going to each one of these permutations, and we're counting the number of colorings that are fixed by that permutation. And the way we're doing that is we're simply saying, look at each one of the cycles and put a color on that cycle. Everything else is automatically going to be determined by whatever you color one of the vertices or one of the edges or what have you. Okay? What if you wanted to 3-color stuff? Well, now you can kind of see how this is going to work. Okay? Let's kind of, let's erase this and let's think about it again. If we were going to 3-color, look, you would say, okay, what about this guy right here? Well, how many colorings are fixed? Well, I have 3 colors here. I can choose here, 3, 3, 3, right? So there's 3 to the 4th total colorings are going to be fixed by that permutation. Okay, what about the cycles? Well, this guy, all right, this guy and this guy. Okay, think about it. They're going to each, once I choose a color, we're done. All of the other vertices have to be colored that same color. So those two guys together give rise to the 2 times 3 that's sitting right there. Okay, which is analogous to the 2 times 2 in the second summand for the 2 coloring case. Okay, what about the 2 times 3 squared? Well, the 3 squared comes from this guy, or 3 times 3 squared. So it's 3 squared, this guy, right? It's going to be 3 squared because it's 3 for the first cycle and 3 for the second cycle. And then again, I have a 3 squared sitting right here. Okay, and that all 3 of those account for the 3 times 3 squared thing that's sitting right there. And then these two guys right here, right, those are 3, right, those are going to be 3 cubed. Okay, and those guys account for that. Okay, so 3 to the 4th is 81, 2 times 3 is 6, 3 times 3 squared, that's the same as 3 cubed, is 27. 2 times 27 is 54. Okay, so what am I going to get? 81 plus 81 is 162 plus 6 is 168. And if I divide that by 8, I get 21. That's amazing, okay, that I can count the number of 3 colorings of this thing. Okay, hopefully you're starting to see a pattern emerge, before our very eyes. Starting to see a pattern emerge before our very eyes here. This is fantastic stuff here. You can kind of tell what's going to happen. If I was going to, for instance, 5 color these things, you just say, so what would it be? So you just kind of think it through, right? So what if I were to 5 color? So the number of 5 color, if I were to 5 color, the number of distinct 5 colorings would be 1/8. Okay, and what would it be? Well, I would stare at the identity permutation, and that would be 5 to the 4th. Plus, okay, how many 4 cycles do I have? That is cycles of length 4. Well, there are 2 of those, right? So it's going to be what? 2 times 5, right? I just have to choose a color, and that's the end. Okay. So what about 2? So far I've done the identity, and I've done these 2 guys right here. Okay. Now what about these guys? Okay. Okay, the 2. So it's going to be 5 times 5, 5 times 5, and 5 times 5. So this is plus 3 times 5 squared. Okay, plus, okay, what's next? Well, I just have these 2 guys left. Okay, that guy and that guy. Those are each going to contribute a 5 cubed. Okay, because it's 5 for the A, 5 for the BD, 5 for the C. Okay. So it's 5, so it's going to be 2 times 5 cubed. Okay, whatever that is. We can compute that now. But you can kind of see that if you were to do K colors, let me just kind of write it up here. So K color, the K color situation, now we can see clearly it would just be 1/8. Okay, it would be K to the 4th plus K to the 4th plus what? 2 times K plus, okay, 3 times K squared plus what? 2 times K cubed. Okay, so it seems like all I have to do is know the number, I have to know the number of cycles, and I can straight up figure out how many colorings are going to be fixed by that given permutation. And that's it. That's all we need to know. We're going to be able to pull this off. Okay, so, so let's see here. What are we going to do to kind of generalize this? Well, I'm actually going to pause this just because, I want to upload smaller videos here. But we're going to actually look at how to generalize this And we're going to come up with something called the cycle index polynomial. Okay, so I'll be back soon. So clearly we need to keep track of the number of cycles in a given permutation. Once we know the number of cycles, we know the number of colorings that are going to be fixed. The number of colorings that are going to be fixed by that permutation, right? Again, the permutation is an element of the group. We want to know how many things this thing fixes because of Burnside's theorem, okay? So here's a little notation that we're going to be using. We'll write xj, x sub j to the I to represent a product of ij cycles, okay? And in j cycles, a product of ij cycles, okay? So a j cycle, this just means a cycle of length j, okay? So, okay. So, all right, so this will give us a polynomial with a whole bunch of sub-indexed variables, and these things are going to be raised to various powers, okay? So let's write this thing. This, by the way, this thing is called the cycle index. I like to call it the cycle index polynomial. Because it really is a polynomial, after all, okay? So let's see here. What is the cycle index polynomial for the group above? Well, the identity permutation, okay? The identity permutation had a bunch of cycles of length 1. How many of them? 4. Okay? It had 4 cycles of length 1. So we write x sub 1 to the 4th. Okay, so this corresponds, this guy right here corresponds to the 0 degree rotation. Okay, the 0 degree rotation. Okay. Then we had the 4 cycles. Okay, those were the ones that were just complete 4 cycles. How many of those were there? Well, there were 2 of them. Okay, there was A, B, C, D. So this right here comes from 90 degree rotation. So A, B, C, D, and then A, D, C, B. That was 270 degree rotation. Okay, so there are 2 of those. And by the way, there's a little invisible 1 up here that we just don't write down because it's not in, you know, because why? It's a 1, right? Okay. What about products of 2 cycles? We had a couple of permutations like that, didn't we? Okay. What were those? Well, there was the horizontal and the vertical, right, reflection, those 2 guys. And was there anything else that did that? Well, I think 180 degree rotation also did that. So there are 3 of those, okay? Because there it was like A goes to B and C goes to D. That was like the vertical reflection. And then there was A goes to D and B goes to C. That was the horizontal reflection. And then in 180 degree rotation, A went to C, C went to A, and B and D flipped back and forth. Okay, so there are 3 things going on here. So there was vertical, there was horizontal, and what was the other one? 180 degree rotation. That's what those 3 things were. And then finally, we had a couple of permutations which were basically 2 1 cycles, which is why this is raised to the power 2. 2 1 cycles and a 2 cycle. And those were these 2 things, right? Remember, it was the, you know, slope -1 and slope +1 diagonal reflections, okay? So there is our cycle index. There is our cycle index, okay? And what's interesting is we can kind of see what we would have to do to get the answers that we got above. You see this? So like this 2 right here is this 2. Okay, this 3 right here is this 3. Okay, and this 2 right here is this 2, of course. Okay, and of course that 2 is the same as that 2, and this 3 is the same as that 3, and this 2 is the same as this 2. So how in the world would we use this cycle index polynomial to actually get the number of colorings, to get the number of colorings in general? Well, you would take this cycle index polynomial and you would simply plug in all of the x's equal to the number of colors. Okay, and then you would have to divide by the size of the group. Okay, so okay, once again, I mean, just check it out. If I plugged in 2 for x1, and I plugged in 2 for x2, and 2 for x3, and 2 for x4, I immediately see that I'm going to get exactly the formula for 2 coloring the square with the group acting on it. And similarly, if I plugged in all the x's equal to 3, I would get the 3 colorings. And then we would also, if I plugged in 5, I would get the 5 colors. If I plugged in k, I would get the number of k colorings. Okay, so we still want to keep this thing as general as possible. I know that we could have, in theory, used the same letter, but we really do want to keep the cycle structure kind of separated out. That will help us later on when we go to actually write down an inventory for these things. Okay. But, okay, so the thing that we want to point out here is that if I plug in, what's what I said, if I plug in xj equal to 2 into our cycle index and divide by the size of the group, I get the number of 2 colorings. And similarly for plugging all of the xj's equal to 3, okay? Okay, so I mean, in general, what we have here is n, okay, so the number of k colorings is equal to 1 over the size of the group, and it's going to be pg, and what you basically do is you just plug in k, 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 right? You just plug k in for each one of the variables, and it automatically gives it to you. The orbit structure demands it, okay? So that's an amazing thing. We use psi, and psi, which counts the number of colorings fixed by a given permutation, was really the key for us to discern this systematic approach to actually counting the number of colorings fixed by a given permutation. Orbits are the key. Okay? Orbits or cycles are the key. Okay? All right. I'm going to pause this for now, and we'll come back and do a bunch of examples.